All right, hello everyone, welcome back. Did we have an amazing time today? Nice, good to hear, good to hear. Well, we will now start with a little bit of a presentation of our beloved jury here. They will give the solutions to all the problems. Then afterwards we have a small talk again from ICPC and our main sponsors, and then we will start with the award ceremony. So without further ado, I will give the word to Paul from the jury. I will switch it.
All right, thank you. So we will start with the solution presentation. And I have a clicker, that's good. So we had a lot of people on the jury this year from all countries, part of the region. We also had a bunch of test solvers who found some inaccuracies in the problem statements, helped us get them into a, I hope, pretty good shape for the contest today. So yeah, big thank you to them as well. And with that, we jump into the solution presentation. So we go through the problems roughly in order of difficulty, and you will notice that up there in the top right, we also have a statistic showing all the submissions during the contest in different colors. So green is accepted, red is wrong answer, orange I believe is run error, and pink is time limit exceeded, or the other way around, I'm not exactly sure, and then the last hour is in light blue because that's part of the freeze, and we still want to keep up the suspense for the scoreboard reveal. So, problem I, what was this about? This was about the classical FizzBuzz problem that probably everybody of you has seen before at some point. So, how does it work? Let's quickly recap this. So we go through the numbers from some range, but whenever we get a multiple of numbers A or B, we replace them with appropriate strings. So multiples of A get replaced by fizz, multiples of B get replaced by buzz, and multiples of both get replaced by fizzbuzz. And now we were asked to solve the reverse problem, so we were given the sequence, and we needed to figure out what the parameters A and B were. And the first thing to realize there is that this is actually two independent problems, so you can consider the fizzes and the buzzes separately. So you first find all the positions where a fizz is, including those with fizzbuzz, and the same for the buzzes. And then you need to handle three separate cases. The first of which is if there's at least two occurrences, then you just take the distance between the first two of these, and we were guaranteed that the input was valid, so that's just the step length. If there's only one occurrence, then what we can just say is that, okay, we think this is the first one, so we just take that number, output it, and we're done with that case. And finally, there's another case where the fizz or the buzz just does not occur in the input range, and in that case we can just say the first occurrence is sometimes after our range and output that. There weren't that many pitfalls on this problem. We still found some interesting submissions. So some team tried to use exception handling to determine whether they actually got a number or one of the two or one of the three strings. And it turns out that that was too slow. Okay, and then finally we have the solve stats. So 136 of you solved the problem before the freeze, and 5 teams still submitted during the freeze, and we will find out later whether they got it.
Thank you, Paul. Then for next problem, bottle flip. You were given a bottle with some radius and some height. And you also had some density of air and of water. And then the question was, to which height should this bottle be filled such that we can successfully do a bottle flip? Because we've really been trying for ages in the jury room and didn't happen. Michael made a really nice visualization of this. He drew this himself, actually, so that was nice. One first observation you can make is that the radius of the bottle is not actually relevant because the center of the mass is always in the center of the bottle. So you don't need to take that into account. And you can find the result using a ternary search because the center of mass, depending on the height of the water, is some quadratic function. So you can find the minimum of that using ternary search. And then for the solution, you have these intermediate variables that you can calculate for the center of mass of the water and of air. And then you can get the weighted average of that using this pre-fraction. I'm not going to read it aloud, I'm very sorry. But yeah, like I said, it is also possible to find the minimum of this parabola using some nasty expression that you need to differentiate. This is left as an exercise for reader if you really want to try it at home. But yeah. Before the freeze, 100 teams got an accepted submission, and after the freeze, still 22 submissions were made. Next up, circular caramel cookie, our favorite treat in the Netherlands. So you were given a number of squares, and you needed to output the radius of a circular cookie such that you strictly have more squares than in the input. This strictly more turned out to be a problem for some teams, unfortunately. But yeah, so given this example here, we have a cookie that contains 60 squares. So if the integer that you would be given would have been 59, then a cookie with radius 5 would be fine to get a cookie with strictly more than 59 squares. And one thing you can immediately note is that for a fixed radius r, you can determine the total number of squares that can fit in a circle. And you can do this for every column using the Pythagorean theorem. Because depending on in which column you're in, you can determine the height of that column. And then you can use binary search to actually find the final radius of the caramel cookie. And this takes log s times square root of s time to calculate. It is possible to do this in order square root of s time. I do not know this challenge. Who added this? So that's also left as an exercise for the reader then in that case. Other than that, 89 submissions were accepted before the freeze, and 49 submissions were still made after the freeze. And then next up, Marcus.
Thank you. The next problem was Delft distance. Here we had a city given as a grid containing either squares of size 10 minus epsilon or circles of size of diameter 10 minus epsilon, and we had to find the shortest path from the northwest to the southeast of the map. At first glance, this might seem like a quite continuous problem with the circle, but the first observation you make is that it's actually sufficient to look at these points. Any optimal solution will go through these points and then either along the edge of a building or along the edge of a tower. So there are two ways to then, based on this observation, find the actual shortest path. One is just constructing the map as a graph and then doing Dijkstra. So you have straight edges with length 10 meter or round edges with length 5 pi meters. And then you just run Dijkstra, which takes time, and log n. There's something else you can do. You can notice that in this map, the shortest path will never go up or left. And that way you can find a dynamic programming solution where you go from blue vertex to blue vertex in lexicographical order and then take the minimum between either coming from the left or coming from the top. And that also gets you the correct solution, this time in linear time. Yes? Yeah, that might be correct. Thanks. So, and here you can see some of the test cases we had. Sometimes it's necessary to go through the center of the map. And we tried to find as many tricky cases for that as we could. And in the end, we had 215 submissions, of which 85 were accepted. And then we had 53 in the freeze where we don't know the result yet. And I'll hand over to Jorke.
Right, the next problem was ETA, the estimated time of arrival. And here the goal of the problem was to construct a graph such that the average optimal time from any vertex to vertex 1 is exactly A over B, or you had to determine that it was impossible. Well, we can start with some observations. Firstly, it only matters what the shortest path to vertex 1 is. So all edges that are not on a shortest path to vertex 1 can be ignored. So without loss of generality, the graph is a tree. And secondly, the exact shape of this tree also doesn't matter. The only thing that matters is how far away from vertex 1 you are. So we can even go further and we represent the graph as a list of integers, where each integer determines how many vertices are in a specific layer. This is subject to a few conditions. Firstly, well, there can only be one vertex as a root, so A0 is 1. And secondly, if there is a vertex at some distance from vertex 1, then there should be a path to there. So all the smaller ones should also be at least 1. All right, then when you have such a list, you can always construct the graph back, because you just set vertex 1 to be the root, and for every other vertex, you choose any vertex from the lower layer as its parent. And the total number of vertices is then the sum of the integers in the list, and the average optimal time to reach vertex 1 can be seen from this formula, which I will not read out loud, but it's just some simple linear thing. And then we split the problem into two cases. So either the required fraction is less than 1 or it is larger than 1. If it is less than 1, then the solution is relatively simple, because if there is some vertex in the graph where the optimal time is at least 2, then that average optimal time cancels out against the 0 from vertex 1 itself. So the total average optimal time will be at least 1. So then it is impossible. So this is very simple, because there can only be vertices at a distance of at most 1. So in this case, the list 1A solves the problem, and otherwise the answer is impossible. This results in a star graph. In the second case, when A over B is very large, there are a lot of constructions that solve the problem. It turns out that every fraction is indeed possible. And here is one example of such a construction. We consider a long list of at least 2k plus 1 vertices, where k is like the integer, the rounding of A over B. And we add some extra vertices at depth k. And then the total average, the average optimal time, will be exactly that value of k, which is just slightly less than A over B. And then an idea is, when we move one of those extra vertices to a higher layer, then the average optimal time will increase by a little bit. So if you remove enough vertices to the higher layer, then eventually we will reach some point where the average optimal time is exactly A over B. And this is one example of such a construction, and as I said before, there were several others. Overall, there were 196 submissions, of which 62 accepted. And then I continue with another problem, Ragnar. Problem 8, which was the goal is, given a binary tree, you have to determine the minimal number of leaves that you should remove to make the tree strongly balanced. Where strongly balanced means that for every vertex, the left subtree and the right subtree have a height that differs at most 1. And well, a simple idea might be to just check everything. So for every vertex, you compute the heights of its left and right subtree, and then in the subtree that is too high, then you remove all the leaves at the very deep, the deepest leaves, to obtain an answer. But that takes O(n) time per vertex, so overall n squared, and that is too slow. So you need a smarter idea. And the smarter idea is to compute everything at once, using some DFSs. So what we will do is we will first determine the maximal height that any subtree starting from some vertex can have, and then we will move all the vertices to obtain that height. So we start with just determining what all the heights are using a single DFS, And then we set a value for the required height for every vertex. So if we have some vertex with vertex V with children L and R, then the minimal required height that the left subtree should have is the minimum of either the height it already has or the height of the other subtree plus 1, because, well, it can only be at least 1 higher than the other subtree. And finally, what the required height of its parent is minus 1, because, well, the parent should still satisfy its required height, so it cannot be higher than that parent. And the same thing holds for the right subtree. And so with one DFS, you can set all those required heights. And then finally, if a vertex has a negative height, then it cannot occur in the tree, so you remove those. And that indeed solves the problem, that where eventually then all the required height work out, because all the leaves have height 0. So overall, this is linear time, and that's just fast enough. We also have some pictures of some of our cases. So here's a nice picture of a tree, and here is a bit larger picture of a tree. It doesn't even fit on the page. Overall, there were 100 submissions, of which 45 accepted so far. And now I hand it over to Ragnar.
Okay, so it is my turn now. Oh, yeah, sorry, thanks. Oh, another picture. I know. Okay, so it is my turn now. I'm pretty tired, so I hope this is going to make sense. I hope this is going to make sense. Otherwise, you can download the zip. It will come online maybe later today, maybe this week. You can download 500 megabytes, and somewhere there's a README for each of these problems. So in this problem, we're given a set of intervals. Oh, actually, I should mention, in the test session, we had this picture with a coffee cup and a strobe waffle. Then in problem C, a bite was taken. We would have liked in this problem if the strobe waffle had disappeared, because it was stolen, but we were too late with this idea. There was also a storyline about this rubber rub, anyway. So we have these n intervals, and for each interval, we want to find the longest chain of intervals that are larger. First, you can know that an interval can only be contained in another interval if the other one is larger. So we can sort them by decreasing length and just check all the longer intervals and see if it's contained, and then just add 1 to the value of the longest interval it's contained in. This gives a quadratic solution. It will be too slow. So we need to do something better. What we can do is we can sort by increasing left point and then by decreasing right point. So this basically means that while processing, the left can only increase. So this naturally is contained in all the previous visited intervals. But we have to check whether the right point is also less than the right point of intervals we considered before. We can kind of now make a stack or a map or a priority, a segment tree or a Fenwick tree probably works. That contains for each right endpoint the maximum chain length of an interval's ending there. And basically, this can only decrease. So for a larger R, we will always have a smaller value of this. And then once we find a new interval, we find like at the right endpoint, the first right endpoint that comes after this, that's the first one it's contained in. And then we add 1 to that length, and we add this thing into this stack or priority queue or whatever. Yes. And yeah, you have to maintain some invariance there. So some figures. This is like the red has value 1, then value 0. The blue has value 1 from bottom to top. This is another test case where there's super long chains. Here's another one where it just looks like a nice mountain pattern, but there's like lots of these chains kind of interleaving. Thanks. Let's see. And we have 130 submissions, 42 accepted, 36 unknown. Okay, it's me again. So now we have this going in circles problem. You're in a train, with some number of carriages, but you don't know this number of carriages. And in each carriage, there's a light. It's either on or off, and you can move left and right, and every time you move, you get told whether the light is on or off, and then you can toggle the light. And now we need to determine the number of carriages in at most 3 n plus 500 steps. You have to be careful because n is the actual number of carriages, not the maximum number. So our first solution here that uses capital N, where capital N is like 5,000. Like you can do this in 3 times capital N by doing just, you walk through 5,000 steps, turn everything off, then you turn one of them on and you walk back until you hit that one again after going back in the circle. That takes like maybe 15,000 steps, so it's too bad. another thing, you can kind of do an exponential search variant of this. You can choose some number x, walk x steps and clear everything, make 1, 1, and then walk back until you see that 1. But maybe x was too small and you need to double it. And you can double it again and again. If you do this, you get a solution that's something like 8n or 9n, which is too bad, but you can do a bit better. If you exponential search, you can first try 10 positions to the right, then 20 positions to the left, then 40 positions to the right. You get something that's like 4.5n, I think. But you can see this is too much. Oh, I should press this button a few times. Oh, wow. There were so many submissions on this at the end. So this doesn't work. And in fact, we got many people saying, you know, is this right? I think I hacked the problem. I can do it in like n plus 50. And yes, that's the intended solution. So now if you were at BPC, you can guess what I'm going to say. It's randomization. So you randomize. You just put a random pattern of size 25, 35 at the start. So you put some random bits, and then you keep walking to the right until you find those bits again. And then if your bits were actually random, you can be pretty sure that you made a loop. So you have to be careful. If you choose any pattern of length less than 15, we included that pattern in the test data using the Bright sequences. If you use C and you didn't seed your random number, if you just call rand modulo 2 and do that 20 times or something, it won't pass. Some team did it and it failed. If you put some kind of small repeating bit pattern, it will fail. If you put 1, 2, 3, 4, 5, 7, 8, 9 and then down, it will fail. If you put digits of pi, it will fail. If you put digits of e, it will fail. I don't know if people run into this, but we had fun doing this. We were debating whether we should, but this is a lesson. If you want random input, just hammer keys on your keyboard. It's probably more random. Don't put 3, 1, 4, 1, 5, 1, or whatever. Yes, I think that's going to be on this slide. Don't put patterns. Oh yeah, and you have to be careful. If n is very small, maybe you need to handle this case separately. But you can write this solution generically. Like you just write the first 25 bits or something, but then while writing, you always already read them. And if once you like read the pattern you wrote, you're done. And this can work for n super small. You can also handle it separately because you have 500 bonus steps. Yes, let me know if you found like a deterministic solution that's faster than this bound. But I think it can only be done using randomization. Yes, so about 1 submission per team. 40 accepted before the freeze. Let's see how many got accepted in the last 5 minutes. Next up is Paul.
All right. So, problem K. Problem K was about throwing a party and inviting some guests, but all these guests had very particular choices about what kind of toppings they want on their pizza. So specifically, we need to prepare this pizza, which will have some fixed number of slices. And we also know for each slice which 2 toppings are supposed to go on that slice. The only thing we need to figure out is in what order we should arrange the slices around the pizza so that we can prepare it in a very specific way, where we take out each of the toppings at most once. And then we can spread it on some consecutive segment of the slices. Yeah, so we should do this and also make sure that all the topping choices are satisfied. Note that it was possible for some guests to choose the same topping twice. So the first insight you need to make is that this is actually a graph problem in disguise. And you can model the pizza slices as a graph like this. So a slice with 2 same toppings is just a self loop on that topping, and if you have a slice with 2 different toppings, that's just an edge between the 2 nodes corresponding to those toppings. Okay, after you make that observation, then how do you actually solve the problem? So first, you can notice that if any of the nodes has at least 3 neighbors which are not leaves, then the answer is impossible. So let's think about why that is. So suppose we have some node 1, it has 3 neighbors, 2, 3, and 4, and they also have some other neighbor, which is drawn here. So in terms of slices, this means that we have the 3 slices corresponding to the 3 edges in this diagram. And we also have 3 other slices where there's one topping that is 2, 3, and 4, and the other topping is some number that is not 1. Then let's try putting them onto the pizza. So we start with the 3 slices that have topping 1 on them, and we put them somewhere on the pizza. And then no matter how we put the other 3 toppings, it will always happen that the ones get separated in some way. So that means there's no solution in that case. Once we made that observation, we go to the remaining cases, and it turns out then you actually have a fairly particular set of graphs or class of graphs that still remains. The graph may consist of several components, but there's only really 3 kinds of components. One of them is just isolated nodes, which are very far on the right here on this picture. And then the other 2 components are essentially either cycles or just path graphs, with the caveat that each of the nodes on the path or on the cycle can have some self loops attached to it, or some extra edges coming off of it. And yeah, to see why, you probably need to go back and forth between the graph representation and the pizza slice representation. But once you figure that out, what do? You find all the components and determine of which type they are. And probably the easiest way to do this is just do some flood fill to find the components, and then also count in each component how many nodes, edges, and self loops you have, and then you can distinguish the components based on those numbers. Then you should remove all these isolated nodes, because after that, it turns out that there's only 2 cases in which the problem has a solution. One of them is if there's only one component, then we can walk through that component and print the slices in some order that is going to work. If not, then it only works if every component is a path. So all of that can be checked. And then pitfalls, there's a lot of them. So isolated vertices, I already mentioned, is something that can trip you up. Also, if there's paths that consist just of one single edge, that might be tricky. If there's one extra node that only has an edge attached to it, that might be an issue. And one thing I completely glossed over during this whole discussion is that each edge might actually be duplicated, and that might also trip up some solutions. There's probably way more ways in which you can get this wrong, which you can also see from the statistics. So we got 155 submissions. Only 13 of these were accepted before the freeze, and there were 90 submissions during the freeze, and I can already tell you that not all of them were accepted. Okay, I'll hand it over to Marcus.
Okay, now we're moving into the really difficult problems. Last guess, we had a game of Wordle. I hope I don't have to explain what Wordle is. And the word had length L, and we have already made all but one of our guesses, and we need to find a valid final guess, where by valid we mean that it's compatible with all our previous guesses, so we can't know that it's wrong. And to solve this, we think about what do we learn from an already given guess. And first, if we have a green position, that's easy. The given letter must be at that exact position. Second, if we have a yellow or gray position, then we know this letter cannot be at that position. And we learn some more things. First, a letter appears in a solution at least as often as the maximum number over all guesses of the green and yellow positions. And finally, if that letter also appears in a gray position, then it appears in the solution exactly as often as the maximum number of green and yellow positions. So to sum this up, for each letter we have some information. We have a list of positions in which it must appear. We have a list of positions in which it must not appear. And we have a lower and upper bound on the number of appearances. And now we need to somehow find a word that satisfies all these conditions. And to see how we do this, we first consider a simpler version which has all the lower bounds all 0. Of course, this can't actually arise from an actual input because there the lower and upper bound, if the upper bound exists, are always equal, but it will still be instructive to look at this case for this more general version of the problem. And this we can solve using maximum flow. We have a source and a sink, and then we have vertices for all the 26 letters, and finally we have vertices for all the positions in the word. And now we have an edge from the source to each letter with the upper bound as its capacity, and we have a unit edge from each position to the sink, and then we have edges between the letters and the positions, and these are constructed in the following way. For green positions, we have just a single incoming edge with the corresponding letter. For instance, you can see this in position 4 in this example, and otherwise we put an incoming edge for every possible character where we don't know that it can't be in this position. Now this works. The problem is, how do we extend this to also support arbitrary lower bounds? One thing that doesn't work is somehow trying to satisfy the lower bounds first and then try to fill in the rest of the word in some way, for instance, using a greedy approach or something else, because there are ways to satisfy the lower bounds where there's no way to fill it up correctly such that the upper bounds are satisfied. You somehow need to do this in one step. And there are multiple ways to do this. If you have the code, you can do min cost max flow, so you basically prioritize, try to satisfy the lower bounds first, and then try to satisfy the upper bounds with a lower priority. Then you will find a correct solution. Or if you think about it a bit more, you can also find a max flow modeling which does exactly that. Here you have an auxiliary source, and now you have edges from the original source to the letters, and these have as capacities the lower bounds, and the auxiliary source has also edges to the letters, but there the capacity is the difference between the lower bound and the upper bound. So basically all the capacity that we haven't used on the lower bounds yet. And now the trick is to define the correct capacity for the edge from the sink to from the source to the auxiliary source, and there we will put the capacity to be exactly the difference between the length of the word and the sum of all the lower bounds, which basically says that you may only use the auxiliary source as many times as you don't need after satisfying all the lower bounds. So you still force all the lower bounds to be satisfied, and then the excess can be distributed, but only in the way that satisfies the upper bounds. And out of the 82 submissions that people made, we had 4 correct before the freeze, and we'll see how many more after the freeze. And I'll hand over.
All right, so now we get to the last 2 problems, the problems that hadn't been solved before the freeze. So problem A by Bjarke, who sadly couldn't make it here. We're given a list of integers, and we're going to sort it using this parallel sorting algorithm, where in the first round we swap all the odd pairs if they're in the wrong order, and then in the even rounds we swap all the other pairs if they're in the wrong order. So a simple solution that was submitted many times, but turns out to be too slow, is just simulation. You just, it's not too hard to see that it takes at most n or n plus 1 rounds or something. And in each round you can simulate in n steps. So you have an n squared solution, but it's too slow. So now here is like the critical observation. This is like the more insightful observation. After this there's still a lot of work, but let's see. So let's say the last swap is from x to y. So x and y are consecutive numbers. And before this, y is the larger one. Before y is in front of x, and then the last swap fixes them. So when I say fix, it means they get to the right position, and they don't move anymore. So now, if we replace all numbers at most x by 0, and all numbers larger than x by 1, and we compute the time to order this thing, it takes the same number of steps. And from this, we can see that if we try this for x equal to every of the numbers in the input, and we take the maximum, that will be our answer. This 0-1 trick has been at a World Finals problem like 15 years ago or something. You can find it. Something about a black box sorting algorithm, I don't know. Also sorting. Okay, so now the question is, how can we incrementally solve all these 0, 1 instances efficiently? I'm not going to go into too much detail. Please check the README. I'm too tired for this. So if we have a 0, 1 instance, let's say the x's are zeros, they move left, and the dots are 1, they move right. In each step, there are also parity issues. Like in the first iteration, maybe nothing moves, but then after the first iteration, the leftmost x that's not just in its right position will move to the left. So you can see that the top left x, it starts moving left. So time is vertical. So the top is how the zeros and ones or x's and dots are distributed. And in every iteration, some of the x's move left. And it always is the case that the rightmost 0 is the last number to get to its right position. In fact, every iteration, only one of the zeros can get to its right position. And we say that as a 0 is congested when it can't move because there's other zeros in the way. So you can kind of see this queues of more than 2 x's, and that's when they can't move because there's another position in the way. And now what you can see is that the rightmost x, it gets to its position, and we can compute this number from the last time it was congested, from the last time it was waiting. And you can see this queue that goes from the right middle to the top left. And basically this queue is the one that's the bottleneck. And we can compute the time that this queue is resolved from the position of the first x in this queue in the top. So this first x in the queue gets to its position after 4 iterations or something. This is something you can compute relatively easily, just a distance away from the target position. And in every iteration after that, 1 additional x gets to its right position. And so we can take the maximum over x's of all these time to get to its position plus number of x's following it. And you can do this using a priority queue, a segment tree. It's not very straightforward, but you can figure it out. You have some homework, you know. I don't know if there's going to be another slide. Oh yeah, okay, well, sorry. Yeah, so basically, now this is for one instance, but then every time you increase x, so you basically change a few of the zeros into ones. And you can update the segment tree incrementally, and this can all work out. So yeah, so let's see if this was figured out by anybody. In the freeze, it was not before. And then the last problem, which also wasn't solved before the freeze.
Yeah, the final problem was geometry, and there you were given you were given n axis-aligned rectangles, and you need to check if there's a line which touches or intersects all of them. So, and first, if you look at such a line which goes upwards, we can see that it passes below all those red points and above all those blue points. And for lines with a negative slope, so we would need to look at the other corners of the rectangles. And now if we look at the convex hulls of the corners we just marked, we can see that the line we are looking at passes through them. So it separates them. And we can observe that such a line touches or intersects all rectangles, so that's fine. And we can also observe that if it would have been inside the convex hull, there would be a point below it, so it wouldn't touch all rectangles. So a solution exists if and only if it separates those convex hulls. So what we need to do is we compute the convex hull of our upper left corners and lower right corners, and then we need to check if they intersect. And for lines with a negative slope, we just look at the other corners. And depending on how you implement the intersection test, you may need a special case for vertical lines, but just be aware of that if you want to implement it. And the total running time of this is n log n, and that's just for sorting when you compute the convex hull. And yeah, for the fun facts, we got many clarifications which asked something about a laser, but we as a jury, we don't know what a laser is, as the problem statement only defined a hull beam. So I don't know what you guys meant, but yeah. Now, for even more fun, we draw you some test cases, but yeah. Example for this, there is a solution, but if you try to find a line which goes through corners, you have really many corners you can try and you won't find a valid solution, but only if you try corners from the middle square in that case, you can actually find a solution. So if you try to brute force it by finding a line, by first choosing a corner where it has to go through, you will have a hard time. Yeah, there are even more cases just for the fun. Well, so there were 29 submissions and 0 of them were accepted before the freeze, and we will see if the remaining 26, if any of that was correct. So back to Ragnar.
All right, so that was it for the problem solutions. We go to some more random statistics and story time. What's the fuzz? So there were very few submissions in C and Kotlin again, a few in Java, a few in Python, but again, mostly in C++. We can see that people programming in Java relatively had more wrong answers than accepted. In C++, you had more accepted than wrong answers, so that tells you which language you should use, maybe. Java didn't have run errors there. C++, out of bounds, I don't know. What else can we see? Time limits didn't have in Java, only C++. Let's see. So we had 720 commits. I don't know, probably 2 days ago this was more like 500. We'll get to that. We had 1,400 secret test cases, over 100 per problem. We really went out of our way to hammer your submissions. We thought the set might be too easy, so we made it more difficult with more test cases. Yeah, it's more than twice more than last year. Some team asked about whether the judge queue was full for the submission to F. I can tell you it was not full. We just had 200 megabytes of test cases, 200, something like this. Okay, we had like roughly similar number of jury solutions. Now is the fun part. We always compute a minimum number of lines of code you need to solve this after code golfing. It's only 13 lines per, what? It's only 13 lines per problem. It's like way easier than last year. I don't know why it was so hard, guys. Fun fact, the team from Artec here was the only team to beat us, I think. Or like only on problem J, our submission was not so short, but you guys made the shortest solution of everybody on that problem. So congrats. Yes, this is, like we missed some kind of these simpler solutions. We only had segmentary solutions, so yeah. Some of the work we put in, so it's story time. Michael mentioned that on F, you could try quadratic solutions that just iterate over all pairs of points and then break as soon as you find a line that goes through one of these points. Actually, if you did this on Friday evening, on Saturday morning, this quadratic solution would have passed in half a second. And so most of yesterday, we spent making more test cases. Yes. So, okay, yeah, most of our time is spent on a small part of the problem set. Oh, okay. Well, also, if you're like grammar police, if you care about Oxford commas, if you care about nodes versus vertex, if you care about illustration versus figure, if you care about, I don't know, super consistent problem sets, join our jury. We want you. It takes so much effort. I think, yeah. You might not notice this, but we try a lot of effort into being extremely consistent. If you see the word vertex in a problem, you're going to see the word vertex throughout our problem set. We only use the word node if it's about a data structure, basically. Anyway, yeah. If you like this kind of stuff, join us. If you like to make test cases, also join us, please. All right, I wanted to say more about F, actually. So, yeah, some of the pictures you saw before, we made them yesterday to, like, this quadratic submission now takes 1,000 seconds or something, and it's actually implementing this quadratic solution correctly also took 5 hours of our time, just because actually it's a very simple idea, but these interval intersections are just super hard. So you can see the number of commits basically doubled since 2 weeks ago. The number of secret test cases doubled since 2 weeks ago, and it went up a lot in the past 2 days. The number of jury submissions also, I mean, there's just some quadratic submissions at the end you see there. Also, it went down because we removed some of the problems from our set. We always start with like 15 problems, and then it goes down to 11 or 12. Yeah. I don't know. I think that's it for this. It is. So we go. So, yeah, I hope you all enjoyed the problem set. Please consider joining the jury. We had a lot of fun making it. It was a very tiring process in the end, for me at least. But yeah, I hope you enjoyed it, and see you next year from my end.
All right. Thank you so much, jury. Then I would like to invite Veronica for a small closing speech from ICPC. Yes, they will be after you.
Okay, how are you, everyone? I started my talk with how are you doing, so I want to hear how are you doing now. So I will not take much time because I know that we are all eagerly waiting to see the results, and it was so much fun to see this problem solution. So first of all, I would really like to thank all the ones who organized this event and made it possible. So I would like to thank all the problem setters and judges. Let's give a big round of applause to them. I would like to thank all the coaches and, of course, all of you participants, because without you, this event would obviously not be possible. So let's just give a big round of applause to each other. Huge thanks to all the volunteers who were behind the stage, and I had brief chats with them. I don't know how many times they were running up and down all the staircases, just keeping fit and bringing like balloons, printouts, and having this event, making this event possible. So a huge round of applause to all the volunteers team that are still in the building somewhere. To the host, which is the TU Delft, and we are hoping to be back soon, actually next year, because TU Delft will be hosting the next year event, and I'm sure to meet many of you here. And of course, thanks to the sponsors, without whom this event would never be possible, and I would encourage you to meet them after these awards in a more informal atmosphere. You know, both Huawei, JetBrains, they will be there, so please just come and chat and ask many questions that you didn't have chance to ask maybe before. And really just keep doing what you are doing. Like it's been amazing being with you here all these days, and thank you for your hard dedication, motivation. It's very inspiring, and looking forward to have more and more teams. So please encourage your friends to join this regional contest and join you possibly at the NWERC next year. So thank you so much everyone, and I will not take too much of your time as promised.
Hello, everyone. I'm Ding Ding. So I don't want to occupy most of your time here, since I know you are eager to know the final results, including me. I'm eager to allocate the Huawei electric devices for the winners finally. But what I want to say is that I just want to congratulate you all to participating in the NWERC in the past 2 days. It's a very precious experience to you all. And I must say thanks for the ICPC commit that I am say thanks for all the participants and the coaches and the organizers and the volunteers for your efforts. And thank you all, and enjoy in the events. And wish you can, and it will help you improve your skills and gain it and make the new friends here. Thank you.
Right.
Thank you. Okay, first of all, congratulations everybody with the completion of this wonderful contest. I was watching how the results were changing, and it was really dramatic and interesting and unclear until the very last moment. So congratulations, great job. Second, I would like to say thank you to organizers, because it was an ideal organization. One of the best events I've ever seen. Very good job, thank you. The, the only thing I doesn't like at this contest is that in this statistic, amount of problems solved in Kotlin is 0. I really encourage you guys, girls, to take a look to this language. It's probably better suited for what you're doing than Java or Python. I wouldn't compete with C++, but congratulations. Thank you.
All right, you can stay on stage. Okay. All right, I would like to invite all the representatives from Huawei and JetBrains to come on stage, and also the Gypsy to start the resolver, the exciting part. Wil jij die... Oh. Can I? Yes. All right. Okay, we will start first with the company teams. So also excitement for that. There was a strong rivalry going on between the company teams. So I'm very excited to see what the final scoreboard is for the company team. So can we start it? All right. This is ook gelijk de scoreboard, right? Okay. On place number 6, we have Fox IT. Congratulations. Okay, volgende. Then on number 5, we have ASML. Then on number 4, we have CWI. Place number 3, we have Ortec. Oh, place number 2 is IMC Trading. Oh, and the first place is Jane Street. I would like to invite Jane Street to the podium, please, to the stage. Yes. Congratulations. Ooh. Congratulations. Congrats. All right, let's make a quick picture and then final applause. All right, thank you. Then we will now continue to the resolver for the contestants. It's loading still, so a little bit more exciting now. It's like, ooh, yes, all right, nice. Then we will start now with the resolver. Okay. You can explain it?
Okay.
Yeah.
So, well, first, because we have a lot of pending submissions, 533 in total. We're just going to go by the first few quite quickly. We'll stop, of course, with the first solved. But around the top 20, we'll start doing the ooh-ah thing. If probably you're familiar with it. If not, if we have yellow submission, then we'll do the ooh, and if it turns green, then we'll either clap. If it turns red, we'll say ah. So, but we'll do that around like the top 20 just to keep it within time limits. So, all right, bear with us.
All right, here we go. Oh. Ooh, ah, ah. Oh, we're going quickly. Yes. Hey. Hey. Ah. Hey. Ah. Hey. Hey. Ah. Hey. Hey. Ah. I hear like all the hey, We're having a good tempo here. Hey, 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 It's kind of sounding like a soundtrack now. We're making a beat here. Hey, 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 hey. Hey, hey. All right, we're now slowly nearing the top 50. Hey. I see some very creative names over here. Hey. Hey, 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 hip hip hurrah! Hey, hey, hey. All right, we're now going slowly to go to the top 30. Oh, it's getting a little bit more quiet. I think the excitement is building, right? All right, we have first to solve problem B. Congrats! And we continue. When is there going to be a hey again? Hey! All right, now we're going to go slower. We have near the top 20. What is it going to be? Jacob's rules? Hey! Kindergarten time limits? Oh! One more try? Yay! Chill clip on place 17? Hey! Oh! Exponential Fenwick on place 15. Trinity's Trinity. Ooh! Hey! Ooh! What's it going to be? But first to solve the balloon animals, very creative name. Ooh. All right, I'm out of breath, guys. All right. Ooh, ah. Last one, maybe. Ooh, ah. But place number 12. So that means that we have here our first bronze medalist. And first to solve problem E, please come to the stage, the balloon animals. All right. Yeah, they are coming. They first need to shuffle through some other people, but slowly we're getting here. All right, congratulations, the balloon animals. And the coaches are also invited to come on stage with their teams. So if there's still a coach somewhere? No? No coach? Oh, okay. Yes, you can. Yeah, go ahead. Go ahead. Also. Yes, you. Let's do the pictures all together. So you just give it. All right, let's take a picture all together. Yeah. Yeah, all together. We're trying to make it fit here. All right, thank you very much. All right, what is it going to be? Ooh, ah. But congratulations, whatever, for place number 11 for a bronze medal. Please come to the stage. Is team whatever still here? Ah, yes. Congratulations. Yes. Yes, if you can come a little bit. All right, thank you so much. All right, Sekvold go brrr. Ooh, ah. But congratulations, Sekvold go brrr for 10th place. Please come to the stage. Congratulations. Yes, you are showered with gifts here on the stage, so it's very difficult where to look. All right, congratulations. All right, then for the last bronze medal, who is it going to be? Lame, lame? Well, are they gonna be lame or not? No? Ah. Ooh. Hey! All right, then one more try. Congratulations with bronze medal. And first to solve problem H, please come to the stage. Congratulations. All right, thank you so much. Now we continue with the silver medals. So congratulations, standard string name is equal cat team name. Woo! And first to solve problem J. Congratulations.
Thank you. Congratulations.
Thank you so much. Then we will continue with Trinity's Trinity. Ooh, hey! All right, but then I would like to invite Tsatsiki Tartares for the silver medalist onto the stage. You know, it's always, every contest that I present, it's always a challenge to pronounce all the team names correctly. So if I don't pronounce it correctly, I'm sorry up front already. Congratulations. Oh, this is a challenge. I'm already not that long, so... Thank you so much. Congratulations. All right, thank you very much. Then for the next, we have Kexi Fan Club. First to solve problem G. Please come to the stage. Also bringing the whole collection of balloons. Very nice. As we already told you, the goal of the contest, balloons, medals, prizes, having fun. Congratulations. sorry. Congratulations. Congratulations. Ah. All right. Yes? Thank you. All right, now for the last silver medalists. The owl. Please come to the stage. Congratulations. 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 Oh. Congratulations. Congratulations.
Oh, did you get the gift? Two coaches? They have two coaches.
Yeah.
5 people.
Yes.
Moeten we naar voren?
All right, thank you. Now we will continue with the golden medalists. So, Lame, congratulations with 4th place. Please come to the stage. Congratulations. 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 All right, thank you so much. Then we will continue with 3rd place. What is it going to be? Ooh, ah. Yeah, so now for the name pronunciation. Yeah, congratulations. First to solve problem D. Please come to the stage. Congratulations.
Thank you.
Congrats. Congratulations.
Thank you.
Congrats. If you can step a little bit. All right, thank you. Okay, for 2nd place, EZCP. First to solve problem C and L. Please come to the stage. I don't know what happened here. We had to mix up with the pictures. Sorry for that.
Congratulations. Congrats. Thank you. Congrats.
Congratulations. Yeah. Thank you so much. And sorry for the picture. All right. Then, congratulations, Trinity, contest winner, first place, winner of group participants, first to solve problem F. Please come to the stage.
Thank you. Thank you.
There you go, congratulations. Congratulations.
Thank you.
Congratulations. All right. Then I would like to thank you all so much for coming to this weekend at NWERC here in Delft. We're so proud to have hosted this event here, and we hope to welcome you all next year here again back in Delft. And I would like to give one final applause for all the organization, everyone involved here to make it happen this weekend. So thank you. Yeah. Thank you so much. There will still be drinks in the Central Hall, so I would like to invite all of you to the Central Hall to still get some nice drinks.
Take another smoke straight to the lungs, yeah, I feel the pain, coffee.
You